Welcome to lecture number 110 of Digital Electronics. In this lecture, we are going to deal with asynchronous counters. So what is basically what is asynchronous counters, which is depending on a specific modulus. That is, here I am going to design an asynchronous counter so that it can count from 0 to 5, for example. It can count from 0 to 10 or 0 to 12 or 0 to 15, like that. That means it is basically a modulus counter. So going to the first question. Design a mod switch, or it is also known as modulo switch. That is similar to the case of synchronous counters. Modulo switch asynchronous counter. Modulo switch asynchronous counter using asynchronous counter. Now, what is meant by modulo switch? Modulo switch means it can count the states 0, 1, 2, 3, 4 and 5. Okay. And again it counts 0, 1, 2, 3, like that it will count. So here you have 6 states. That is why it is known as modulo switch counter or mod switch counter. Now, generally in asynchronous counters, we are using T flip-flops. We are using T flip-flops in general for asynchronous counters. Now, let me come into the concept of that. Concept of this mod switch counter. So, coming to the concept of mod switch counter, see, 6 states. That means the final state is 5. So, you have 1, 0, 1. If you are finding the binary equivalent of 5, you have 1, 0, 1. Now, when it reaches 6, it should be 1, 1, 0, but 6 is an invalid state. 6 is an invalid state. That means at 6, it should reset. At 6, it should reset. So that is the basic concept behind a modulus switch counter. Again, to represent these 6 states, you need 3 bits. Because 5 is a 3-bit number, so you can go for 3 bits. Therefore, 3 flip-flops are required. Now, before going into the logic circuit, let me draw the truth table of that. So you are having 3 flip-flops, that is Q3, Q2, Q1. Okay. 0, 0, 0, 0, 0, 1, 2, that is 0, 1, 0, 2, 3, 0, 1, 1, 4, 5, that is 1, 0, 1, 6 and 7. Now if you are writing the decimal equivalents, here, this will be 0, 1, 2, 3, 4, 5, 6 and 7. Now, what is the concept I have already mentioned? When it reaches 6, you should reset it. So you should have a reset pin or a reset input. So at 0 it is 0, 0, 0, 3, 0, 4, 0, 5, 0. At 6, reset should be equal to 1. And at 7, it can be either 0 or don't care. That means it is resetted means it is set back to 0. Resetted means when 6 is the state 6 comes, it is resetted to 0, 0, 0. That is 0. Okay. That means it is resetted to this state. That is what is being done here. Now, coming into the K-map. That means here we need to derive an expression for R in terms of Q3, Q2 and Q1. So I am going for R. So I am going for here. I am having Q3, Q2, Q1. 1, 2, 3. So this is there. So here having 0 and 1. So 0, 0, 0, 1, 1, 1, 1, 0. So 0, 1, 2, 3, 4, 5, 6 and 7. At 6 it is 1 and 7 you can take it as don't care. For all other elements it is remaining as 0. Now how you can club? You can club it in pairs. If I am clubbing this pair, here which is common, Q3 is common, and in these two what is common? Q2 is common. So you can write reset as Q3, Q2. And you can give either reset directly or R bar. If it is R bar, you will get Q3, Q2 bar. Okay. Now, why I have written R and R bar? If you are directly giving to the clear pin, there is a clear preset and clear. If you are giving to the clear of flip flop, you should give R. And if it is given to the clear bar, you should give it as R bar. Okay, that is the basic concept here. So you got R bar as Q3, Q2 bar, and if it is clear, you will get reset. Reset R is equal to Q3, Q2. Now, how to draw this? Again, here I am going for negative edge triggering. Negative edge triggering flip flops. And again, I am using T flip flops. I am going for T flip flops. Now see, here, how should be the order? That is the next question. How T1, T2 and T3 should be arranged. See, the variation of Q1 is fast. That is 0, 1, 0, 1, 0, 1. That is this point. That means T1 should be the first flip flop. T2 should be the next flip flop. And T3 should be the third flip flop. So now I am going for T1. So I am going for T1. You will get a Q1 bar. Now coming into T2. T2 you will get Q2 bar. Coming into T3 you will get Q3 bar. So for all T's, inputs are is equal to 1. Inputs are is equal to 1. Now it is negative edge triggered. So clock is given here. Here also it is negative edge triggered. So Q1 is directly given here and Q2 is directly given here. So Q1 is taken as one output, Q2 is taken as one output, and Q3 is taken as one output. Now suppose I am giving into clear bar. Here I am having clear bar. What is clear bar? Clear bar I have got the expression as Q3, Q2 bar. So I am going for Q3, Q2 the whole bar. And I am connecting it to all clears. I am connecting that to all clears. Okay. So here I am having. Okay. So your logic circuit of asynchronous counter is over. Now let me come into the timing diagram. Okay. So I am having the clock. Clock is applied to flip flop number 1. So this is flip flop number 1, flip flop number 2, and this is flip flop number 3. So I am going for clock of flip flop number 1. Okay. So I am having 1, 2, 3, 4, 5, 6, 7, and 8. I am having 8 clocks. Since this is negative edge triggered, I am going for these edges. Negative edge triggered means I am going for these negative edge triggered edges. Okay. So initially my Q1, Q2 and Q3 I am taking it as 0. So I am having, now I should start from Q1 only. Then I should go to Q2, then I should go to Q3. So I am having here 1, 2, 3, 4, 5, 6, and 7. So Q1, Q2, Q3. All are initially equal to 0. Now first let us check for Q1. So Q1 will be toggling when it is, because T1 is equal to 1. At negative edge trigger it will be changed to 1. At this it will be changed to 0, 0, 1. At this point it will be changed to 1. And at this point it will be changed to 0. At this point it will be changed to 1. And at this point it will be changed to 0. Like that it will go. So you have at this point. Now what is Q2? Now coming into Q2. In the case of Q2, what is acting? Q2 means Q1 is acting as a clock. So you are having negative edge triggered, negative edge triggered, negative edge triggered. So here you have 0, 0. Here you have 1 up till here. Then you have 0 up till here. Then you have 1. Like that it will go. Now coming into Q3. Now coming into Q3, here what happens? When coming into Q3, let us check. So here what happens is that Q2 is acting as a clock for Q3, so it is negative edge triggered here. Okay, so 1 and yeah. So this is becoming Q. That means at this point and some other point. So I am taking 0, 0. Up to this point it is 0, and after that this will become 1 for a longer period of time. Now let me write in Q3, Q2, Q1 order. Okay, I am writing in Q3, Q2, Q1 order. So initially it is 0, 0, 0. 0, 0, 0. Then you have 0, 0, 1. 0, 0, 1. 2, that is 0, 1, 0. 3, that is 0, 1, 1. 4, that is 1, 0, 0. And 5 is 1, 0, 1. Now, at this point, I am applying a reset. That means at this point, I am applying a reset. That means reset is up to 0 up till that point. Reset is 0 up till that point, and at that point I am giving a small reset pulse. Okay. When it is a reset, what happens? All Q1, Q2, Q3 becomes equal to 0. So you have to cut this part. You have to change this part. Okay. So at this point, what happens is that Q1, Q2, as well as Q3 becomes 0. Q1, Q2 at this point. At this point it will become 0. Okay. So that is how reset is happening. So reset pulse is given for a small time. That means when it reaches 6, it is resetted. So next state is it will come to 0, 0, 0. So here reset becomes 1. When it reaches 1, 1, 0, reset is 1. So at the instant when it reaches 6, it will be changed to 1. Okay. So this is basically the timing diagram. Okay. So that is regarding this mode 6 asynchronous counter. Now coming into next one more modulus counter we will deal in this lecture. That is, we are going for mode 10 design, a mode 10, or it is also known as modulo 10 asynchronous counter or ripple counter. Asynchronous counter, this is also known as ripple counter. Okay. Now if I am going for these asynchronous counters, let us see what happens. So I am taking only T flip-flop. I am considering only T flip-flop here. Now let us see what happens. So that I have Q3. Mode 10 means I should count from 0 to 9. 9 means 1, 0, 0, 1. So at the instant 10, that is 1, 0, 1, 0, I should reset. So I have Q3, Q2, Q1, Q4 is there, and at that point I should get reset. 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll get 1 here. This 9, and at 10 we should get reset is equal to 1. Okay, so we should have 0 in all other cases. 0 is there in all other cases. And if you are writing the decimal equivalence here, you will get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At 10 reset is equal to 1. And for 11, that is 1, 0, 1, 1, you can make the reset as don't care. And up to 10, up to 15, reset is don't care. Now we need to derive the expression for R. That is the only case what we have here. So I am drawing the K-map. You go for 4 variable K-map. Go for 4 variable K-map. So here what we have is Q4, Q3, Q2, Q1. This is a reset. 1, 2, 3. 1, 2, 3. Here having 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Now reset is 1 for this, 1 for 10. For 10 it is 1. For 11, 12, 13, 14 and 15 it is don't care. And for all other elements it is remaining as 0. Okay. Now one question, how you can club? So you can club it as a quad. So you can club it as a quad. If I am clubbing as a quad, I will get like this. So here which is common? Q4 is common. Here which is common? Q2 is common. So you can write reset as Q4, Q2. Reset is equal to Q4, Q2. Therefore we can write R bar. Either we can give R bar as Q4, Q2 bar if we are giving to clear bar pin, or if you are giving to clear pin directly, you can write it as R, that is equal to Q4, Q2. Now coming into the logic circuit of that. Okay, you are having, initially you will have T1, Q1, Q1 bar, negative edge triggering. I am going for negative edge triggered. So I have clear bar here. So this is clock T1, T2, Q2, Q2 bar. Then comes T3. T3 is Q3, Q3 bar. Now comes T4. T4 what I have is Q4, Q4 bar. All are negative edge triggered. All are negative edge triggered. Okay. So Q1 is counted here, Q2 is counted here, Q3 is counted here, and T is equal to 1. T is equal to 1. Now what is going into the clear bar pin? That is what we need to judge here. Clear bar, clear bar. Okay. So here what is coming out? Q1 is coming out. Here Q2 is coming out. And here Q3 is coming out. And then comes Q4 is coming out. So what is clear bar? Clear bar is Q4, Q2 whole bar. Q4, Q2 whole bar. Q4, Q4, Q2 the whole bar. That is given to all the clear pins. This is given to all the clear bar pins. Okay. So that is the logic circuit of mode 10 asynchronous counter. So already, if you are drawing the timing diagram, you should draw for Q1, Q3, Q3, Q4. Up to 9 it is same, and at 9 when 10 comes, it will get resetted. Okay, that is something similar to this one. Okay, that is something similar to this one. Okay, so that is regarding what? That is regarding modulus 10 asynchronous counter. Okay. So that is all regarding this one. And here what happens, the only thing is when 10 arrives, you will get the reset. Okay. So that is regarding mode 10 asynchronous counter. So in this lecture we have designed with modulo 6 asynchronous counter as well as mode 10 modulo 10 asynchronous counter. Okay. So here how basically an asynchronous counter functions. All the flip-flops should be in toggle mode, and if it is positive edge triggered, Q1 bar should be connected as clock of next flip-flop. If it is negative edge triggered, Q1 should be connected as clock of next flip-flop. Here I have gone for negative edge triggering, that is why Q1 is connected to the clock of next flip-flop, and Q2 is connected to the flip-flop of flip-flop number 3. Q3 is connected to the clock of flip-flop number 4. flip-flop number 4. Okay. So I think you got the concept of designing an asynchronous counter in especially up-down counter, up counter, and down counter. And in that I have mentioned about this positive edge triggering as well as negative edge triggering. Thank you.